Hello, and welcome to Lesson 3 of this Introduction to Linear Algebra with Wolfram U. The topic for this lesson is row reduction and echelon forms. So let's begin with a brief overview of the lesson. So here's a matrix, and it looks like it's got pretty random entries. Some are large, some are small. And the goal of this lesson is to transform such a matrix to a simpler echelon form. That's like a much more ordered set of entries. So you see over here, this looks much more orderly than the earlier matrix. So for example, you go to ones along over here, and the last column looks like it's got some very interesting and useful information. So the question is, how do you obtain an echelon form? Well, an echelon form can be obtained by using the process of row reduction. And fortunately, we have a very nice function called row reduce in the Wolfram language, which will give you the reduced echelon form of a matrix like the one you see over here. And the point is that once you have this reduced echelon form, you can solve linear systems. So let's begin with a formal definition of a reduced echelon form. So a matrix is said to be in a reduced echelon form if it has a few properties. The first property is that all non-zero rows are above any rows with all zeros. So you can think of the rows with all zeros as being kind of redundant, so you don't want them to be on top at all. Next, the leading entry in each non-zero row must be 1. So you always start with a 1 in each non-zero row. Next, each leading entry of a row is to the right of the leading entry of the row above. That's where the word echelon comes from. It's like an orderly arrangement, like troops of soldiers in an army. And finally, you want each leading one to be the only non-zero entry in its column. So here's an example of a matrix that is in a reduced echelon form. You can see over here the zeros are all at the end, and then every row begins with a 1. And if you look at any column with a 1 in it, then that's the only non-zero entry. And the fact is that every matrix has a unique reduced echelon form, which can be found using row reduce. Okay, so before going into row reduce, let's just look at an example of how you might actually find the reduced echelon form using elementary row operations just by manipulating the rows and getting the answer. So here's a matrix. You want to reduce it to echelon form. So what you do is you take the second row, R2, and then you do R2 minus twice R1. So that becomes 0 over here. And then after that, you divide by -3 to get that to be a 1. The -3 becomes a 1. And then you still want to make that 5 into a 0. So you do row 1 plus -5 times row 2. So you get a 0 over there. And finally, you do row 3 goes to row 3 plus row 1 minus row 2, and you get back this nice echelon form. So you can check the answer with row reduce, and you see that you get back just the same result. Okay, so let's try and use row reduce directly. So here's a matrix. The matrix has 3 rows and 4 columns. Apply row reduce to it, and sure enough, you get back a reduced echelon form. But you see over here that this echelon form is so much nicer in structure than the matrix that you began with. Okay, a slightly larger example now. So here's a random 8 by 9 matrix. I use a seed random to just make sure I get roughly the same answer every time. So here's the random matrix with 8 rows and 9 columns. I apply row reduce to it, and what you get back is a very nice, simple form. So once we know how to use row reduce, we can now talk about solving linear systems. So the question is, how do you solve a linear system using row reduction? Well, the steps are, you first of all write down the augmented matrix with both the left and right hand sides for a system, apply row reduce to it, and then looking at the output from row reduce, you can write down the solution set. And in fact, there are 3 possibilities. The first possibility is that you actually have a unique solution for your system, just one solution, or you might have infinitely many solutions, and both those are said to give you a consistent system. And the third case is where you have no solutions, and that's referred to as having an inconsistent system. So just to summarize and make sure we understand terminology, you can either have a unique solution, or you can have infinite many solutions, or you can have no solution at all. So one example of each. Here is a system of equations, a linear system, 3 equations, 3 unknowns, x, y, and z. So you first of all set up the augmented matrix for system, make sure it looks right. So you have 3, 5, 11, 46 in the first row, that looks correct. 2, negative 3, 4, 8, second row, and 1, 6, negative 7, negative 38 in third row. All that looks just right. Okay, then you apply row reduce to it. Look at the matrix form, and now it's clear that this first one over here is just a placeholder for x. So x is 1, that's a y, so y is 2, and that's a z, so z is 3. So x equal to 1, y equal to 2, z equal to 3 is a very nice, simple, unique solution for this system of equations. Okay, so on to a slightly harder example where you actually have infinitely many solutions. So here's a system. Write on the augmented matrix again. Make sure it looks right with matrix form. So for example, the first equation is 5x plus 2y plus 11 is equal to 4. So you got 5, 2, 11, 4, etc. Apply row reduce to it. Look at the matrix form, and you see that the last row is just a bunch of zeros. That says you actually have infinitely many solutions. So the question is, how do you write them down? Well, this first row here says that x is negative 25z plus 10 because the z goes across the right hand side, and y is 57z minus 23. So for each value of z, you actually get a value of x and a value of y. So for example, if z is 1, then if you plug back over there, x is negative 15, and you plug back over there, and y is 34. So in fact, you have infinitely many solutions, each one corresponding to a different value of z. And the question is, how did this example come about? Well, what I did was I simply took the first 2 equations over here, and I added them, I summed them to get the third equation. So 5 plus 7 is 12, 2 plus 3 is 5, 11 plus 4 is 15, and 4 plus 1 is 5. So the third equation is in fact redundant over here. It's got no new information, and hence you actually have infinitely many solutions to that system of 2 equations. So that's one way you might get infinitely many solutions. The question is, can we then go ahead and construct an example where you have an inconsistent system? Like, can I make this slightly different to have no solutions at all? Well, I could just make the 5 into something else, and that's exactly what I do on the next slide. So I take the first 2 equations, but I replace the 5 by a 6, and that's going to give us an inconsistent system. And the sign of inconsistency, you have a row that looks like zeros all the way up to the end where you have a 1. So that says 0 equal to 1, which is never possible. So here's the system. Write the matrix for it, the augmented matrix. Look at the matrix form. Make sure it's all okay. It does look okay. Apply row reduce. And you see over here that the last row is 0 equal to 1. That's no good. There is no solution for this system. But of course, we knew that. We just constructed the way we wanted to make sure that there is no solution. So the 6 over here made sure that there is no solution. So this is a system which has no solution. Okay, so that brings me to the end of this lesson. And the main point is that every matrix can be reduced to an echelon form by using elementary row operations, which are nothing but what you would do if you actually solve the equation by hand. Namely, you could, let's say, interchange 2 equations, or you might add one multiple of an equation to another, etc. So those are called elementary row operations. And of course, within the Wolfram language, we have a nice function called row reduce, which will let you do much more and get to the reduced echelon form in no time at all. Now, the point about this row reduction is that it can be used to determine whether there are any solutions at all for a for a system and how many solutions are there. So row reduce and row reduction are a great way to solve linear systems. Of course, row reduction is a bit more technical than using linear solve, but it's a very powerful way of understanding linear systems. So that's the end of this lesson, and next lesson we'll talk about vectors in n-dimensional space. But do review this very important lesson on row reduction, and I hope you have enjoyed it and learned a lot from it. Thank you very much. I'll stop over here.